we were discussing the first step of the initialization, which is turning on the clock signal that is being fed to the digital port. And from the datasheet, we've seen that without feeding a clock port, we won't be able to change anything on the control registers, well, which makes sense. I mean, this is a register, and if you want to change a flip-flop's value, in Barbarossa's course, you'll remember that, well, a clock needs to be fed to the flip-flop so that any value could change. And actually, these control registers are a bunch of flip-flops or similar designed digital circuitries, whatever. So in order to be able to do anything, we should first feed clock to the device. And we've learned that there's a specific register for it, not on the device, but on the microprocessor. So the architecture is like this. Let's say this is port F. This is port F. I'm going to draw something to, how can I put it? Make it, for you to realize it, imagine the clock comes in like this. So there's a clock here. There's a clock here, the system's clock. So the clock, this is the clock. It goes, and you want to connect this clock here. So what happens is, imagine you have this. The clock is being connected to I'm writing this name here. Pin 5, this is called R5, connected to it. So that single pin is connected. So this is an AND gate, guys. And if this is 1, clock will be fed. If this is 0, the clock will freeze. So this is something like this, very simply put. So there must be a register in the microprocessor like this, and the clock and this pin of that register is being connected in an AND gate, which is connected to the clock of the pad. So if it's a pad, this is the clock entrance. Clock entrance. So this must be something like this. I always try to get to the architectural idea behind so that you understand what's going on. And what we're trying to learn is how to do it in code. So remember, how do I reach here? Does the assembly language understand this word? Actually, no. We will have to make it understand. They're all of them are some 32-bit addresses. And we know each address because it was written in the data sheet. And we introduced these, we can introduce these names to the compiler in the code using EQ. So as you can see in line 35, I've done this. EQ. And remember that was the value. Good. So if I do this, I can do the first line. Let me do it in code. And this is the code, guys. As you can see, this is the code. Let me show it on Kale. So guys, this is Kale. And as you can see, this is the part of that code. Let me go up and read the directives. As you can see, it's already defined here. Okay. So what does this code do? Regarding your friend asked a question, how to do it. He couldn't exactly figure out how it's done. Well, now we have R1 pointing to this location. Okay, R1 pointing to that location. So R1 is the pointer now, and R1 is pointing to this sys blah blah register. I am making LDR R0 R1, which means this 32-bit register, R1 is pointing to this 32-bit register. It means, hey, go to where R1 points, read that value, and write it inside R0. So the values of R0 will be, sorry, the things that is written in this sys GTL whatever register is being written into R0 first. I save them to R0 at this line, So then I make an OR operation with the values inside R0 with this value. What is that value? So in R0, I have 32-bit values, right? The first 24 bits, because I have read this from system control. And remember, system sorry, where is it? Yeah, it's here. System control was this, and the most significant 24 bits are all reserved. They don't have a value. Actually, they are zeros. And I've got these values. So let me get to the point. So in R0, I have 24 zeros. Then I have the value of R5, R4, R3, R2, R1, and R0. They were called R5, R2, R0, remember? R5, R4, each bit. So guys, I'm going to AND this number, or this number, because this is OR register. This is bit-wise OR operation, OR register with this value. So this is 20. So this is 20 means the first nibble is all zeros, zeros, zeros. And this is 2, which is 0, 1, 0, 0. The next is, since I don't write and doesn't matter, 0. When you make this operation, guys, OR operation, what happens? ORing with R0 with 0. When you OR something with 0, what happens? You get itself. Any questions with this? Because if you OR 1 with 0, that's 1. If you OR 0 with 0, it's 0. So it's itself. Whatever R0, I don't know. When I OR it with 0, the result doesn't change. It's still R0. Any questions? R1.
Hocam biz şimdi R1'e bu ilk başta tanımladığımız şeyden kaynaklı mı bütün register'lar R0'nun içerisine yazıldı?
Well, there is no way that you can write a single part of a register. That's why we are transferring all of them, because we cannot get only one value of a register. We can only transfer all of them from register to register. That's why. But we are going to change only one bit. That's what I'm talking about. So guys, R0, R1 with 0, ORed, it's R1. So whatever value here, the same, the same, the same, the same. R5 ORed with 1. What is the result? I don't know the value of R5. It could be 0 or 1. What is the result?
1.
1. Whatever the value of the result, because this is 1, it will be 1. So it is like, guys, this operation is changing these register values only at this bit to 1, but not touching the rest. Only making this bit 1. Because we want to make this bit 1. Why? Because if you make this, if you make this bit 1, this one 1, it says in the data sheet that, let's find that data sheet. It says that enable and provide clock to port GPIO port F. That's what we are trying to do. Okay, good. So I've got it in R0 now because I ORed them and I've written to R0. Now I make the reverse operation. The values of R0 to point where R1 points. R1 is still pointing this location. The values of system control clock have changed. That's how I change it. Any questions? Something very simple, but this is the first time you're seeing it. That might confuse you, but you're going to get used to this. Any questions? Good. So somewhere on the microprocessor, there was this bit, and I made it 1, guys. This one, let me show you. This one, I made it just, this is 1 now. And because it's 1, the clock that is being fed is enabled, guys. Okay, let me just clear all the drawings. Okay, now there is an information which is written somewhere in the data sheet that I won't show you exactly now, but there is one thing you need to know about enabling a clock to this digital pad. The clock, when you feed it, will take a little bit of time for the device to start itself because you're feeding the clock to all its registers. And you need to wait for a couple of cycles. So actually you're doing no operation here. No operation means at this clock, microprocessor doesn't do any arithmetic logic operation. It waits for the clock to pass. So it's a single clock operation. I do 3 of them so that I don't have to do 3 of them. I need 2 of them, because when you make this register one, actually, the digital pad, this digital pad here, starts to get clock. But it's a digital circuitry, and the guys who have designed it realized that it needs 2 cycles to properly start working. That's why in your code, you put these no operations so that you wait for 2 seconds doing nothing. The digital pad gets ready, because after it's ready, I'm going to change some registers on the digital pad. This register is on the digital pad. So it is like I'm giving clock and waiting for 2 seconds. It's ready now, and I'm doing my job. How do I know this? This is written somewhere in the data sheet. I just cannot find it right now, but it is written somewhere in the data sheet. Any questions about the idea of waiting for 2 cycles so that the device gets ready? Guys, you're going to come across these kind of things a lot. I mean, you're going to read the data sheet and it will say, well, just enable that pin and wait for the first cycle to complete because blah, 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 blah. Digital programming is all about understanding this, I mean, intrinsic properties of the device and making it work by obeying those instructions. And that's what we are doing right now. Guys, we have done the first step. The first step is done. Sorry. We're doing this. We have done this. At the first step, actually, this is, so it is here. We have done this. This was the first step. This is for the switches. We're not going to do this. This week's context is all about getting the LEDs work. So we're not going to use the switches, so I'm going to skip this. We are going to learn this later. Then I'm going to disable the analog mode of this pin, because the LEDs are digital devices. The analog mode of those pins should be disabled. There's a register for that here. Where is it? It's here. It's here. Yeah, it's here. I'm going to change the analog mode selection registers. So where is it? It is somewhere in the data sheet. You should go and find the data sheet, guys. Let's do it. Let's. The page is not written this time, but I'm going to show you how to find it. So, for example, I'm going to use the same guy. Yeah, it is analog mode selection register offset. Analog mode select GPIO. It is here. So as you can see, it explains. So port F, it is at this location. And with this offset. And it explains, guys, analog mode select. You can read it. The GPIO analog mode selection register controls isolation circuits to the analog side of the unified I/O pad. I explained this to you. The I/O pad, GPIO pad that you've seen, this guy has both analog component capabilities and digital component capabilities. They are separate circuitries. If you're connecting a digital device, you disable the analog part circuitry. And that's what it's talking about. The isolation circuits, they isolate currents and blah, blah, so that it works. Because the GPIOs may be driven by 5 volts, it explains the reasoning. So what you're interested in is how to use the pins. Again, at this address for port F, so this port F, so let's remember the address of it. So port F is this value. So it is 40 million something. As you can see, it is this guy plus the offset. So it is this, actually, this one. This one. Don't think about this. That's another one. It is the address here. I don't want to get into the details right now. So guys, again, it's a 32-bit register, just like R0, but in some other place, a physical register. It's on the digital pad. The most significant 24 bits are reserved. You don't use them. You have 8 bits. For 8 pins separately, you can select analog mode on and off for each pin separately. Guys, which pins the LED is connected to? Do you remember? So it was PF1, PF2, PF3, right? So if you look, these are PF1. So this is PF0, so F1, F2, F3. So these ones I should change to disable the analog mode. And how to change them? If I make them zeros, the analog function of the pin is disabled. So I'm going to make these pins 0 to disable the analog mode. Okay, I know the address. It's already written in my directives. I know which pins to change. Well, let me do it. Let me do it. How to do it, guys? Okay, so it is written here. So I already have this code, and it is pointing to this address, the correct address. What I do is I read the value. So R1 is pointing to here. I first get the value. So whatever inside R1 is at R0 now. Then I make a bit clear operation. This instruction means clear the bits which are shown in this mask. How does it work? Let me show you. So guys, when you had R1, so R1 is pointing to here. So you have everything in R1 in R0. R0 is now this value, all zeros, 24 bits, all zeros. Then analog mode selection, what was the name for that? It says GPIO. So these are 7. Let me write those as numbers so that you won't get confused. So these are registered 24 bits, 24 bits. And I've got some values here. Okay, let's say that initially they were 1. They were selected. I don't know the initial values, but let's assume that they were 1. Which values I want to change? This one, and this one, right? Because PF1, PF2, PF3, the ones that are connected to the LED. And I'm going to be using a mask to change it. So how to change that? This is 000E. So I'm using a mask. Let me write that number, 00E. So this is E. What is E? E is this, guys, 1, 1, 1, and 0, 0, 0, 0, and the rest is 0. Assume 0. This is 0E, guys. And bit clear operation, I'm defining bit clear operation here. Bit clear means look at the mask, and if at the mask a pin or the corresponding pin is 1, make them 0, clear them. So when you do this operation and write it back to R0, this is bit clear, which means R0, get the mask and write it over R0. These pins will be made 0. The other ones will not be touched. That's how bit clear works. So at R0, I have this value now. Do you understand how bit clear works? That's how bit clear works, guys. This is an instruction, and that's the definition of the instruction. We are learning a new instruction right now. Any questions? Okay, now I have this value. I'm writing the value of bit 0, R0 to R1, which is this. And I have changed this register now. I have 1, 1, 1, 1, 0, 0, 0, 1 at this register, and these are disabled. That's how I do it. Any questions? It will go on like this, guys. This was the next second step. So the third step is another step, the port control, this one. It is here. How to make necessary changes? Well, you go and read the data sheets. So I'm going to find it. Port control, yes, it is here. As you can see, the GPIO PCTL register, it is the short for port control register. It selects the specific peripheral signal for GPIO. It works conjunction with alternative function selection. It means if you don't want to use the alternative function, you have to change this register and this register both. How to change them? It explains. I mean, changing which bit to work. It explains. So this is the GPIO port control register. So port F is here. How to change them? Well, actually, This is a bit strange register. You have to make all, so this one, for example, you have to make all of, so for each pin, there are 4 bits here. So for port F, for each of them, you have different 32-bit registers. This is a 32-bit register. For each one of these addresses you have, and we are going to change this for port F, okay? And if you want to change the necessary ones, what you have to do is, for example, this is for, let's say, port F. This is for PF0. This is for PF1, all of them. This is for PF2. And this is for PF3. That's how it works. So this field, as it says, I mean, this field, it says, this field controls the configuration for GPIO pin 4. So this is GPIO pin 4. And how to change those values? Actually, we are going to make them all ones, zeros, using bit clear. If you make this bit clear, F zeros, so you are making each pin separately 0. That's how it works. I mean, you may wonder why. Why are we doing this? Because that's the design. We are following the instructions which were provided to us in the data sheet. I didn't go into the details of the instruction, this one. I'm just giving it to you because we don't have time for all of those. But in this one, what we do is this. At this point, usually students wonder, well, are we to memorize all of these? No, definitely not. That's not the idea in this course. When you do a project, you'll have to understand it and write your initialization for once. Definitely, you'll have to do it. But in the exams, I'm not expecting you to remember some part of the data sheets. What I want to do is to understand the logic. For example, if I say, to make it work in your exam, I'm telling you this, there's a control register. To make your function work, you have to make the 6-bit 0. You should be able to write the necessary code to do it like this or like this. That's what I expect from you. That's why I'm showing you these examples. There's an instruction to do it, and this is the instruction. So you have the explanations here. Let me get to the code. So this was the GPIO port F. So this is the analog mode selection register. This is the same code. This is the port control register. We have to change it to make port F a GPIO, not an alternative function. The datasheet pages is written here, as you can see. We have the same page we have found. It's here. So what we do is I get a pointer to it. I get the values first to a safe register R0. I clear those necessary bits as instructed in the datasheet, and I write it back. This is similar as this was the case, it was the case. You get the values to R0 first, change the necessary bits, do not touch the unnecessary bits, and write it back so that you get exactly the necessary function you need, but you don't create unnecessary functions in the bits that you don't use, because we are not using PF4, for example. We're not changing any bits which are designated to PF4. Okay? Any questions? Good. Now the next step. Set the direction for these pins. Well, PF3, PF1, PF2, connecting to LEDs. Is this an input or output? Just to wake some of you up, is this an input or output?
Output.
Thank you. That's a LED, that's an output. So I should make these pins outputs. How to make them outputs? Let me get to the data sheets. Do I have the data sheet page? No, I'll have to find it myself. So I say, what is the name of it? Dir. Let's say dir. Let's look at it as dir. Okay, let me find. There are so many dirs. Bulamadık. Gerçek adını bir yazmaya çalışalım. Sometimes the name I use in my codes and they are different. GPIO registers, GPIO registers. Let me find it. Direction. Ah, that's here. Wonderful. GPIO direction register. So it is here, guys, with the offset. So if you sum these numbers up, it is 40,002.500, 5,400. So is that so? Was that the direction register? Yes, 400, exactly this value. Okay, so I've got the correct value. So what it does is, if the corresponding pin is 0, it's an input. If it is 1, it's an output. What I'm trying to do is, I want to make these pins as outputs, guys. So I want these to be 1s. The rest, whatever they are, I don't care. I'm not going to use them, because this is the PF3, PF2 and PF1. This one, and this one. Okay, let me do it. How do I do it? Simple code again. I'm going to, when you try to make something 1, you use the OR gate. I make R1 point to it. I get R0. I get R0 inside. Not the rest of the code is not here, so I'm going to do it. Show it to you here. So it is here, guys. It's here. So when you read it, after you read it, after this line of code, at R0, you have the first most significant 24 elements as zeros because they are reserved, 24 bits. Then I have some values for pins. So I don't know which values. I OR it with 0E. What is 0E? 0E is 0, 1, 1, 1. This is E, 0, 0, 0, 0. And zeros the rest, 0. I make an OR operation. So this is X, anything with 0 ORed, it's 0. When you OR something with 1, 1, 1. Sorry, that's not 0. Sorry. That's X. So when you OR 0 with X, it is X. I don't know what X is, but ORing with something, ORing something with 0 doesn't change it. But ORing something with 1 will make it 1. 0, 0, 0, 0. X, and zeros. So as you can see, in this operation, I only touched these pins, made them zeros, didn't touch the rest, whatever they are, let them stay. Then I wrote it back. So those pins have become outputs for me. Okay. Burada bir line daha var arkadaşlar. Onu niye yazmıyor burada bilmiyorum da bir line daha var. str. Yazayım da dursun. Sonra şeyden bakarken videodan sıkıntı olmasın. str. Altına da yazmıyormuş ya. Ne zormuş bu. Şeyin altında olduğu için. S. Şuraya yazayım ya. str R0 R1 arkadaşlar. Şuraya gelecek. Okay. Good. Now we are halfway the initialization. Good. Next one is disabling the alternative function selection bits. For that purpose, I have this one here, this register here. I'm going to change it. So the previous thing I changed was the direction register. This is okay. I'm going to do this. So I'm going to go somewhere and change some bits. How? Written in the data sheet. Let me find which data sheet. I'm going to look for offcell in the data sheet, and it will provide me the necessary information. Offcell, yes, this is GPIO alternative function select on page 671. Well, as you can see, it is for port F, this number plus this number. Is it so? Let me just check. Yes, it is this number, the correct number is written here. Okay, again, 24 bits reserved. I'm going to be using these bits. I try to make operations only for PF1, PF2, PF3, which is this, and this pins. How to change them? How to change them? Let me say, if it is 0, it is GPIO. If it is 1, it is the alternative function. So I'm going to use it for GPIO. So in that case, I want to make them zeros, zeros, zeros. To make certain bits zeros, you'll remember from the previous examples, we have used this bit clear thing with E because E was exactly pointing to those pins. And I get it to R0. I write it back. And at this port, I have those necessary pins as blah, 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 0, 0, 0, blah. These are PF1 to PF3. So they are zeros. Good. I have this step as well. Then pull-up registers. I don't use these pull-up registers because pull-up registers are some functions for switches, and they are by default deselected. I'm not going to touch these, but next week when we are trying to initialize switches, we are going to change these registers as well. Then digital enable, that's the final on-off button. That's the final off button. I'm going to digital enable this. Digital enable is somewhere. Let me find it. Digital enable is here. I'm going to change this pin. How to change the digital enable? So it is making some pins ones actually. How do I know this? I'm going to find it. Digital enable. Oh, sorry. Enable. Digital enable pin. It's here. As you can see, it is at this location plus 51C. Is it so? Digital enable, that value plus 51C, correct address. So it is, if this 0 it is disabled to digital functions, is 1. So what I have to do is, for the LEDs, make this pin 1, this pin 1, and this pin 1. These ones, I don't care. I don't want to change them because this initialization routine is for only enabling PF1 to PF3 so that the LEDs are connected to it and so that you will be able to make it on. Okay, so I have it. And if I have to make them 1, I will use the same mask with OR because this is like OR. When you OR it with this mask, it becomes 1. When you OR it, use bit clear, you make them 0. And you understand the logic, I guess. And we are finished. We are finished, guys. We are finished with the initialization. As you can see, we are finished. This was for PF, port F LED in it, because port F is LEDs are connected to PF1 to PF3. This is a specific configuration, initialization routine to enable the LEDs. If you run this code before you do anything, your port F will be ready to use the LEDs. Then how to change the LEDs? How to change the LEDs, guys? Well, how to change the LEDs? This digital pad, this port, has 8 pins. So imagine this is port F. Port F. You have PF0 to PF7. These pins, how to output a value? Well, actually, you are going to use GPIO data for it. GPIO data is also a register. It's a 32-bit register, but the first 24 bits are reserved. And the last 8 bits, if you write any of them, and if you configured your device to be an output port by selecting the direction register, we have configured it as an output port. When you write something to it, these pins will change. And what is the value of this GPIO data register? Well, actually, it is written here. It is this, guys, at this location. This is the GPIO data register. And actually, there is something strange. You can connect to this data register using this data, but you can connect to each pin separately with a separate address. This is called the individual pin mappings. I'm going to discuss it later. Let's just see this example for now. So port F data register, let's find the data register. Data registers, data registers. Is it the data register that we're talking? No, this is not the data register that we are talking. Sorry. Data register. GPIO data, right? Exam data registers. I'm trying to find the data register. I guess it was here, guys. In the read example. So it's GPIO data registers. Data register operation. GPIO data. Huh? Okay, it's here. Let me find GPIO data. It is here. As you can see, for each port, you have a separate data register. For port F, you have here. And if you write, if you configure port, for example, port F as a data port, and if you write 1 here, well, you will be writing 1 to that specific register. And to make the LEDs on, we're going to write 1s and 0s here, because this is LED, the red LED, the blue LED, and the green LED. By changing these values at this address value, we are going to change the registers. As you can see, this is the offset is 0, so that's the value. Is that the value? Yes. The data register. It's different. Sorry, that must be different place. So this is the data register. I couldn't find it correctly on the data sheet, but we're going to change these registers. How? Let me show you. So for example, I want to make the LEDs on and only the red LED on. I've written a subroutine. This is a single subroutine. So this is here. So this is a single subroutine. This is red LED on. So it's the red on subroutine. What it does is it first saves the R0 and R1 and it will load it before going out. It makes R1 point to PF1. Let's say PF1 is this register. PF1 is this register. Actually, it's this register. It's a register which is used to connect to the red pin only of port F. That's also a mapping, just like this one. There are different mappings for data registers, guys. And you write 02, which is 00000010, because that's what this is. Port F is the red. And you write this value to R1 and it becomes 1. And after you write this, after this line, the red LED will be on. And we are going to do it next week on the video. We are done. Okay, how to create a color, etc. That's next week's business. Any questions? No. Yorucu bir dersti tabii.